All right, cool. Well, it's one. I guess it's a good time to start. Thanks for coming to my talk, Input Validation in PureScript. For those of you who don't know me, my name's Joe Kachmar. I am a software engineer at WeWork. Right now, I'm mostly writing Scala, but I was in a position where I was writing mostly JavaScript, Python, that sort of stuff for work for a little while, and I started learning PureScript around then and got to even sneak a little PureScript in at work. So hopefully can present a motivating use case for this language that gets some of you people who are using JavaScript a way to maybe use a little more typed FP. I basically came to PureScript from Chris Allen's Haskell programming from first principles. Was really in a situation where I missed strong static pure functional programming, and PureScript kind of delivered. So yeah, actually, let me try and get, all right. So this is what we're going to be going over throughout the course of this workshop. Real quick before we get started, a little bit on what this is not going to be. This isn't going to be a crash course introduction to PureScript, and this is not going to try and be sort of a crash course introduction to all of the types of abstractions you could use in a language like PureScript or Haskell. If you meet someone that can do those types of things in 2 hours, please send them my way, and I will pay the money to train up people to do it, because that's awesome. But what I'd like to try and cover is showing the types of things that these techniques, specifically around using validation and strongly typed abstractions, what we can avoid with them. Mainly trying to validate that your input is correct using Boolean types. I'm going to talk about defining a set of errors and a set of functions that you can use to validate any types of fields that you might want to check for correctness based on primitive types like strings or integers. Going to sort of show how these primitive validation functions can be combined together using some of the type class abstractions that PureScript and also Haskell and Scala kind of allow you to do. Talk about how those can be used to, or talk about how you can sort of represent fields or more complex, richer types that you would want to validate. Show how those primitive validation functions can be combined to validate more richly typed inputs, and then finally show how all of these can sort of come together to validate what you might consider to be a form. This is going to be a exact web form in the traditional sense of that. I'm not going to walk through a web form library, because that would also be just, if I could do that in 2 hours, that would be great, but I don't really know what a good web form looks like, period, let alone one that I can sort of do on the fly. But we're going to kind of maybe try and model what a prototypical web form might be. So, Boolean validation. I mean, I've written code like this. I've written code like this recently. This is not great. You're basically checking, is something correct or is something incorrect, and you're returning a Boolean yes or no answer. You have these validate email and validate password functions. They're ostensibly going to check if maybe you passed it in a string that corresponds to a valid email or a password that corresponds to some kind of rules you want to check. You don't really know why something goes wrong, or like what in particular goes wrong in this case. This is a super simple example. You could maybe dress it up, but really it's mostly going to be ad hoc things you're building around these types of concepts in most programming languages. So it's on you to basically think about how careful you want to be about adding more context to these simple true and false answers. This is pretty similar to, like I said, pretty similar stuff I've written, and it really is awful when something goes wrong and you have no idea why it failed.
This looks too sophisticated to me.
This?
Yeah, instead of having the validate email, you should just Boolean coerce the email address with two bangs.
I mean, it does. It's true. You're probably not going to have incorrect emails if you do that.
But we do know that we have fun emails.
We do. All right, so first step, validations on primitive types. I'm kind of making up some terminology within this. I'll try and maybe say when it's a term that I'm using that I've sort of created for the purposes of this talk. When I say primitive types, I really mean things like strings or ints, pretty much. These don't carry a whole lot of context around what you're using them for, or really just aside from the fact that they represent a very basic concept. The nice thing about writing validation functions on these things is these are going to be like the bread and butter of how you build up complex systems. You're going to always need to check that an int conforms to something. So this is where you really have to start. And so when we start off with the type of validation, as it were. So you can think of the concept of the validation type as either a valid result or a collection of some errors. that are associated with that result that made it not valid. The PureScript validation library, which we're going to be using today, models this idea with this sort of sum type. Anything that's being validated is going to be wrapped in V, and that's going to have the opportunity to contain either errors or that valid result. If the validation functions that you're writing encounter any kind of errors, it'll return the results wrapped in this invalid constructor around the error type. And if it has a valid result with no errors, it'll wrap it in the valid constructor on the right side. This is very similar, almost identical to either, with a couple key differences that we'll get into later that make it its own kind of thing. So specifically, you might be used to, if you're using data constructors in a language like Haskell or PureScript, using them directly as functions to wrap it. The PureScript validation library doesn't expose these directly. When you want to signal a validation error, you're going to use the invalid function. If you're going to signal a valid error, you're not going to use the valid function because that doesn't exist and that's a typo. You're going to be using the pure function, which comes from Applicative. The main reason they do this is because if you expose the data constructors, you could pattern match on them and get the value out inside and then potentially futz with your validation that way. What you really want to try and do is seal all of the indecision around whether or not these things are going to be correct or false in this validation type and provide a single explicit function that PureScript validation calls unv that you'll use to run the validation as it were, and there you're forced to handle or to pass it explicit functions that handle the errors or the successes and then return back a result of some type. So super simple form input right now. This is a PureScript record. We're basically saying we're going to have some kind of form with two input fields, an email address and a password, and we're making a type alias for this form called unvalidated form to express that these have very simple types. You're going to maybe call your input field email address and password, but strings are not what we want to deal with. And this is sort of what we're going to be working with for the bulk of the workshop. So we want to represent primitive errors for this form. We've got kind of the plain English concept of how our errors should be represented on the left-hand side in bullets. And the nice thing about what we can do with a strongly typed language is pretty much mechanically translate that list from the right to a sum type, or from the left to a sum type on the right that's going to be sort of tagging these errors with types. And in the instance of, say, invalid email, too short, everything but empty field, trying to give you some context on what exactly failed. So if we have an invalid primitive, it could be completely empty, nothing, in which case you don't have anything really to give back. You're just going to say there's nothing here. But if it's an invalid email address, you might want to return the string that is the not valid email address so you can, respond with some kind of meaningful input to your user or something like that. Same thing with the other ones. Too short and too long will return an int that is the length of the thing that was not long enough, and then an int of the length that you needed in order for a valid input. As with most things, these could be made maybe a little more obviously expressive if we used maybe, say, records in too short and too long, but this is already gets you a lot more than not having a sum type. So, say we want to make some kind of function that validates the minimum length of a string. This is sort of the type signature of what that function would look like. We have a function called validate minimum length, validates that an input string is greater than some length. It takes an input of the minimum length as an argument, and it returns this v type that we saw from earlier, where the error is a non-empty list of invalid primitives. Why a non-empty list? We know that if we ever get an error, something went wrong. You can't have an empty list of errors. If you've ended up on this left side of the branch, then you're here for a good reason, and you're going to have to deal with that fact. And on the right, we just return the thing that we validated. So we're not trying to perform any transformations. We're just trying to check and see, is this good? And if it is, give back the same primitive form so we can do more stuff with it later. The way that this function is implemented is we take the input as an input argument and the min length integer as another input argument. We use PureScript's guards, which are kind of like, if else you're familiar with Haskell's guards, are the same way. So we say, if the length of the input is less than the minimum input length for a valid string, then we use the invalid function to construct, or we'll go from the inside out. We put length input as one of the int terms for our too short error. We put the minimum input length that this thing needed to have in order to be valid as the other term. We use the singleton function to wrap it in a single element non-empty list, so you have that embedded in the non-empty list, and then we use invalid to say that it is an invalid, it's going to be on the invalid side of v. Otherwise, for anything else, we're going to say that that's valid, it's greater than the minimum length. And so we're going to just say pure input. Just return this input embedded in V on the valid side.
I don't quite understand the point of singleton.
So the point of singleton is that we are going to need to accumulate these errors at some point, and so we want them all to be in some kind of container type structure that allows us to add multiple things together. So we're putting each of these things in a singleton of non-empty list so that when we sequence validations later, we're going to append all of these errors together into one list of errors.
This is as if you would just put it in a list, but it's a non-empty list, so you have to use this constructor function for it.
Yeah, exactly. And yeah, there's going to be also some other reasons for having the explicit way that it's done here a little bit later when we want to do things like swap out the type of container that we're using to get other effects. Cool. Any questions? Seem relatively straightforward. This is the whole function. And all it does is it validates that the input string is greater than some given length that you provided it. So if we take a look at another one, this is a function that is going to very naively check if you have lowercase characters in your input string. So it's going to take a string, it's returning a non-empty list with the primitive errors like we saw before, or the input string that is valid. The implementation is very similar. We use the guard, but we use toUpper to convert the input string to entirely uppercase, and then see if it's equal to just the raw input string. If a fully uppercase form of the input string is equal to the normal form or to the provided one, and we don't care about things like Unicode that are going to make our lives difficult, then we can say that it's invalid because there were no lowercase characters, and we provide the input string so someone can do the processing on it later. Otherwise, again, pure input, just return the same thing as we got it back, or as we received it. Again, the whole function. So, first exercise for us is going to be write a primitive validation function that validates that your input is not empty. You can either go to the link that's up here, which will redirect you to try PureScript, or you can go to the links in the GitHub repo that are in the workshop document. They should both lead you to the same place. For anyone who wasn't here a little earlier, the try PureScript website currently will give you a certificate error. That's a known bug. It's recommended for ease of use that you just ignore it, which I know that's not great. If you really don't want to add an exception for this certificate, the exercises have been provided in that GitHub repo if you want to do a little bit of legwork and follow the instructions to set up PureScript itself. And those should all be in the repository for how you should get it set up. Cool, so how does everyone feel about that one? Got results? Good, yes, no? So very similar to the contains lowercase function, does the same thing, converts your input to lower, and then sees if it's equal to the input. Again, if you do this with Unicode, you're going to have a really bad time of it. So this is super naive. There are definitely more clever ways to handle these for wanting to cover all of the edge cases of strings, which is also in and of itself a whole talk. So I think the really interesting part about all of this is how we actually sequence some of these validations together and combine them using the different type classes that PureScript sort of gives us to express some abstract concepts around this type of stuff. So right off the bat, PureScript gives us this notion of an apply type class. If you're familiar with Haskell, apply and applicative are both covered within Haskell's applicative. In PureScript, apply is really just giving you the apply function, which is given some structure f that contains a function from a to b, and given some structure f that contains a value a, return a value, or return some structure f that contains a value b. So basically apply the function in some structure to some value in that same structure and give you the result in that structure. What this instance is actually saying is the structure, the f as it were, is v of error. So the structure contains the errors that we could potentially be handling, and if we're not on an error side, we'll be able to actually pass or apply some function to the input. So walking through this instance definition, when both the left and the right arguments are invalid, both of these errors get combined using the semigroup append operator. And that's one of the key things about this type class instance for V is we enforce that error has a semigroup constraint, which means that no matter what type you want to make error, it needs to be able to combine in some way using the semigroup operator. In our case, the answer is non-empty list. So we have non-empty list, which has a semigroup instance where the semigroup instance defines list concatenation. So this would concatenate, or it would concatenate two non-empty lists together and give you one non-empty list of all of your errors. Next, if either the left or the right argument is invalid and the other argument is valid, then return the invalid one. We're saying something went wrong and the input failed. So when we combine two different validations using apply, we want to show that the error occurred and we're no longer in a good state. And then the last one is when both the left and the right arguments are valid, we know that valid is going to contain an f from A to B on the left side, and it's going to contain some value on the right side. And so we just apply the function to the value and then rewrap it in valid. Apply defines an infix operator for the apply function. You can call this all sorts of things, splat, TIE fighter. I like TIE fighter because I think that sounds cooler. And that's what you use to basically sequence these things or run them together. So for actually embedding stuff, like I said before, when you want to embed something invalid, invalid. Wow. Inside the valid type, you use the pure function, which is from Applicative, and it just says pure equals valid. So when you call pure, you're really just wrapping it in valid. Same semigroup constraint on error here before to keep it consistent with the previous instance. So this gives us the ability to do things like sequencing primitive operations. So we saw that TIE fighter operator from before. There's another operator that I don't have a clever name for. I mean, I guess right bird. I've heard some people say it because it kind of looks like a bird. All this is really is it's defined in terms of apply. All it does is the function that you're applying discards the first argument and returns your second argument in there. And what this lets you do is it lets you run one of the validations and then say, I know this input is valid. I don't care for it anymore. I don't need it for anything. So run the next one. And if at any point any of these validations returns an error, it's going to accumulate that error in the non-view list and you're going to get an error case back. The nice thing about the way that this function is constructed and the way that it works is that it doesn't enforce sequentiality. So this looks like nice sequential code that goes one step after another. But what this is really saying is explore all of the code paths that these functions kind of give you. If at any point any of these invalid things are invalid, it won't block the next step from executing. It'll still run the next set of validation functions. So you're sure that you get all of the errors that your input could have potentially encountered. So in this case, if this thing is, well, it can't be too short and too long. So if we had maybe, say, a validation function that checked for an empty field and checked for a min length, you'd get both of those errors. It would tell you explicitly that it's an empty field, but would also tell you that it's too short. Any questions from that?
What's the distinction with the previous one we just saw?
The instance?
The regular TIE fighter one.
So the regular TIE fighter takes a function as its left-hand argument and then a value as its right-hand argument. What this does is it basically discards the first value you pass into it. So what this is going to do is you're going to run your validate minimum length, and if it's valid, it's going to discard the valid result and then give you the valid result from validate maximum length. But if any of these encounter an error, it's going to preserve the errors it's encountered in the structure of V and append those on the non-empty list on the error side of it. So another short kind of exercise, go to this URL and there's going to be a all of the primitive functions that I defined earlier on that sum type are going to be defined in that exercise, and all you really need to do is glue them together similarly to how the last function was done. I think the comments actually tell you the criteria that you have to fulfill. Yeah, so you're going to want to write a function that validates that an input contains upper and lowercase characters by using the validate contains uppercase to validate contains lowercase functions from before. So how does everyone feel about that? Got something look good? So this is just pretty much relatively straightforward. Looking at the previous example, it's just combining two of the exact same functions we defined earlier over that input. One of the things to note here is that the type signature hasn't changed, really, or the return type, anyway, hasn't changed at all. This is the same return type, and it has to be because all of these functions have to give us the same thing, really, so that we can be sure that we're getting these validations with the errors we expect and the input that we passed it. And we're going to see how to change that in what that actually allows us to do in a little bit. I don't think we really need a break now. You guys all good to keep going? So, where this stuff starts to get really interesting is providing the kind of idea of a specialized field that encapsulates the primitive validations that we've been doing. Like a string can be, between two minimum lengths, or can contain the types of characters we want it to, but that doesn't really express to the person that's running this code that that string is an email address or that string is a password. And more to the point, we want a way to encapsulate the errors that you can encounter when you're trying to check the validity of an email address or of a password and indicate to the person that this particular thing failed for these reasons. So, how do we want to represent validated fields? We use a new type. New type in PureScript works very similarly to new type in Haskell. Really what it is an opaque wrapper around some kind of type that's already defined somewhere else in your code base. So in this instance, we're creating a new type called email address that just wraps a string. We're creating a new type called password that also just wraps a string. And what new type lets us do is create a boundary between the unvalidated basic input and then the validated output that is explicitly stated to be this thing. It's mainly just so that when you're passing arguments around, you're not passing around string arguments, because that's a really easy way to shoot yourself in the foot. If you pass a function that expects an email address and password, it won't type check, even though under the hood they're basically the same thing. For representing field errors, we're going to use another sum type, similar to how the invalid primitives were, invalid primitives were a sum type of specific errors. Invalid field errors are going to be a set of errors that correspond to a list of the potential invalid primitives that we could have run into. So they're the same underlying type, but the errors are going to be different based on what you actually validate under the hood for an email address or a password. It's very important that here, like with the invalid primitive sum type, that the constructors you use for both the type and the fields are descriptive. I mean, if this is just A, B, C, it doesn't really help someone else intuit what your code is supposed to be doing in a natural way. It's just more stuff. So, this is a little hairy, and we'll walk through it depending on how familiar you are with this. First, you validate your input based on one of the primitive validation functions you have, and you bind that to some intermediate variable. We're going to call it result. Then, you use the fact that v is a bifunctor to apply a transformation function to both the left-hand side of the sum type and the right-hand side of the sum type. And what this is going to do is it's going to say, wrap all errors in the invalid email address invalid field constructor, and then wrap that again in a singleton, so that is also in its own non-empty list, again, so we can accumulate errors again later. However, if that result is on the right-hand side and it's valid, then wrap it in this email address new type so that we signal that what you have is a valid email address.
Why do we need to wrap again? It's already on the list.
What we're going to do is we're going to reuse the same thing we did for the invalid primitives, again, when we want to combine all of the validations together in a form. So we still want to have a list of errors which are themselves lists of errors. Because what you want to try and do is build up a structure where you have a list of all the things that could have gone wrong with your underlying strings, and then a list of all of the things that could have gone wrong with these more rich, complex field types that actually try and delineate the fields of your form.
What is the 3 less than mark again?
So PureScript does not use dot for function composition like Haskell does. Dot is reserved as a special keyword for accessing fields of a record, because PureScript tries to have records that more or less match the underlying JavaScript record. So this is your left to right function composition. There's also 3 right angle brackets, that's right to left function composition. So what this is really is saying invalid email address compose with singleton and then applied to the invalid type.
What's the type of result there?
The type of result there is going to be v non-empty list invalid primitive and then string. And so bimap is transforming the non-empty list invalid primitive to a non-empty list invalid field, and then it's transforming the string to email address. So similarly to how we applied multiple primitive validations to a to form a more complex validation that still operated over primitive types, we can combine these primitive validations before we bind it out to the result keyword, and then leave the rest of everything else we're doing exactly the same. And what this will do now is apply both of these validation rules to your simple input, and then do the same exact wrapping as before. And so in this way, it's very, very easy if you have set up your hierarchy of invalid primitives to just add more rules. And everything will continue to work out pretty much as you intended. You just make another rule that has the same structure, you add it using this applicative and discard or apply and discard operator, and then you don't really change the code that's wrapping anything afterwards. So just like with the other ones too, any error you encounter is going to be collected in the invalid side. Cool. So another short exercise. This is just going to be creating a function to validate a password. So in this exercise link, the new type for password has been defined already, and all of the primitive validation functions from before are available to you. So all you should need to do is basically kind of replicate the thing that was in the previous slide, create a complex validation function for the password field using the primitive fields available. So how's that looking? Pretty good? Any questions? Everyone got something? Cool. So the result for this is pretty much just adding a bunch of the primitives together. I actually extraneously added the parentheses on that last one, so you don't really need them. That's just a typo on my part. But same structure as the other ones entirely. You just add more rules, and you make sure that the way that you're wrapping your output is consistent with the field that you want to validate for it. Yes?
How does the in keyword work?
You are creating that let binding up top, and then you're saying the scope in which that let binding is going to be used. So you could create multiple bindings in that let that'll all be used in the in block below it. Does that answer your question?
Right. Yeah. Now I see.
Okay.
I think they might be missing something. Bimaptics, how did the singleton composed with invalid password work? Because does that like map over the non-empty list?
So what invalid password is doing, so invalid password takes a non-empty list of invalid primitive, which is what we're going to be mapping it over on that left side, and we're composing it with singleton to then wrap that in another non-empty list. And that way we'll be able to do the same thing we did here, but later when we're validating the whole form.
Yeah. Okay.
Yeah.
I thought it mapped over. Okay.
Yeah.
I got the right answer.
Why do we need to validate that it's not empty? We have already validation being done.
You don't necessarily need to do that. You could like, that's just another rule that's applied. You could leave that out and then verify that you don't have the minimum length to make sure that it's not empty. What typically can end up happening is it's, depending on how lazy you are, looking for a non-empty or looking for an empty field error when you're pulling your values out is maybe easier to translate directly to a specific error saying it's empty. You could do the same thing where if the number returned is 0, you return an empty field error as well.
Also, I wonder if we want at certain point to fail fast in certain validations.
So the fail fast thing is interesting. If you wanted to fail fast on certain validations, you actually do not want to use the V type for it. This is a good time to get into this now, actually, because we've covered what applicative and apply are doing here. The most interesting part, if you're familiar with Haskell or PureScript about V, is that it has a very conspicuously absent monad instance. Can't do it. Can't be a monad, because if you can sequence these things in a way that requires that one come after the other, then you are required to have fail-fast behavior. And so one of the ways to do it, if you wanted to maybe get some kind of fail-fast, is convert the V to an either, and then run your monadic sequential error checking function, and then convert it from an either back into a V to compose with other ones. And using this conversion, you can take advantage of the way that the instances are different. The code doesn't even necessarily have to change, really. You could just have your own validation function that does the to either, runs this sequential operation, and then converts it back to V, and you can put it right back in your sequence of functions here that you're using to validate on it.
So, but I wonder, like, what's going to be the final type of the combined function that you use, because if I want to use, like, if I want to use ethers to combine them, I need to convert them to validated to combine inside. Like, I wonder what the constructor's block should be to have types eventually, because if I want to use ethers to fail fast in certain ways, then I'm not allowed to use V, right?
Well, the most validation libraries, and I believe including PureScript validation, will include a helper function that will do the conversion from V to either, because the structure of V and either are exactly the same. They're isomorphic except for their instances. Thank you, Steve, for isomorphisms earlier today. But what you would do is you would just, any function you want to fail fast, you would inside the function as an implementation detail do the conversion to either, take advantage of the fact that the instances are designed to short circuit and fail fast, and then convert back to V afterwards, so that all of the rest of your types are more general, so that they admit the behavior of not necessarily failing fast, and then you can sort of, where you want to, pick and choose how to add that fail fast behavior. If you want to fail fast everywhere, then you can use either instead of V, but you still get this, you can still construct the functions similarly to how this looks, just using either's applicative instance. Any other, or did that answer your question? Any other questions? Cool. So, validations on forms. Really, what we're looking to do here is take these individual fields, and much in the way that a record is a product of multiple individual fields added up together, we want to add up basically a product of all of the individual validations and then get out either a full record product or a list of all the errors that we could run into for each of the fields that we're trying to validate. So we've got this kind of unvalidated form representation from earlier, type alias around a record, and a validated form representation that uses our unique opaque type wrappers around string. Yeah, the way PureScript records work is actually pretty interesting. The email address and password are they are represented by a specific type in PureScript, or like there's a specific type that's used to represent it that will guarantee that we're handling these and using them later. So the record representation for products in PureScript is actually very slick.
Can you elaborate?
So in Haskell, the records are really just, it's a product type where the language gives you a function that you use to access that particular field out of that record product type. If you're not familiar with the product type, it's just a type that contains multiple fields inside of it. So a record is just a product, and you have functions that'll give you those fields back. In PureScript, a record is actually what they call, it's constructed using what PureScript calls a row type, which is a type that can contain labels inside of it that you can use to track what that type wants to track. In this case, what a record is, it's a row of labels that correspond to your record fields and types that correspond with those labels. What that lets you do is it lets you look up the label in a record and retrieve it out without having to generate a function for you, which is much nicer. It also lets you do things like generically program over the record itself, because you can access that information in the row and you can see what fields a record can contain.
So email address is not a function.
Right. So email address here is a keyword that you use the dot keyword to access a field in a record. So what you would do is if you had a record called form that had an email address and a password, you do form.emailaddress. So, type signature of a form validation. Very similar to the other ones. The only difference is that instead of taking a string and returning a string, we're taking an unvalidated form and returning a validated form. So we're going to be doing some kind of transformation of these types, similarly to how we did with the invalid fields. Validates that a form contains only valid fields, and it returns either the validated form or the list of all of the errors you could run into while validating that form. So, function implementation. Walking through this kind of. On the first line, that is how PureScript does record destructuring. And so because the compiler has a way of tracking what fields are contained within a particular record, you can use this syntax to say, bind out the email address field to the email address binding and the password field to the password binding. Below it, on the next line, is PureScript's shorthand for declaring anonymous functions. So what in Haskell, this would be a lambda of A and B to constructing a record where the first field is A and the second field is B. So this is just a function that takes 2 arguments and returns a record that fills those 2 fields in with those arguments. This is a shorthand they stole from Scala. It's kind of nice. What we do next is we use the infix keyword for map to take that function and partially apply it to the first result of our validation within V. So we say we want to validate the email address, and we're going to give you the email address string that we pulled out from the unvalidated form, and we're going to partially apply the function that takes 2 arguments to construct a record to that first validation. And so what you're going to get out of this is a V of the form errors you could potentially get, so a non-empty list of invalid fields. And on the right-hand side, instead of having a concrete result, you're going to have a function that takes another argument and fills in that password field of the form. Below it, it's fully applied using the applicative operator, which takes that A to B in the structure of validation and fills it in and gives you a fully applied function within the validation context. So what you get out of this is the ability to build up incrementally your validated form from individual fields that are going to be in the structure of V, while you guarantee that any of your errors that you run into are going to be accumulated on the invalid side of V when you're running it.
Quick syntax question. The deconstruction that you do here with email address and password, does that have to match the validate form record as it was defined, the type?
Yes.
And the validate form is like it's a function that the first argument is necessarily email address because that was the way it was written.
Right. So So the deconstruction here is, what's important to note is the deconstruction here is on unvalidated form. I have made those 2 unvalidated and validated forms have the same keyword names. And this is actually a very important distinction with Haskell. I can do that. I can have 2 records have the same name that I can use to access a field within them, because these aren't functions. And these accessors don't need to be uniquely named functions that correspond with a specific thing to get out of a field. They're really just a way of saying, look up this keyword in this row of types and pull the type or the value stored at that keyword out and give it to you. So the destructuring needs to be done with the same names as the record fields, and then the structuring again below, the anonymous function that creates the validated field, needs to be done with again those same names.
The structuring, like the first line of the function, that structuring is because it is the validated form. Like
Right.
It infers that that is actually the validated form constructor.
Right. So all validated form is it is a type synonym for a record that contains one label, email address, and another label, password, that correspond to the email address and password new types respectively. So this is really basically a way of saying break down the structure of the record, get at the simple types, and then build up the structure of the validated record using these validated types that we have. Any other questions?
What is the 060 again?
So the validate password function that was defined earlier took 2 integer inputs, and that's just supposed to be the minimum length and the maximum length. You should probably have a better minimum length than 0 characters.
Is this like an analog function for mapn in Scala?
Sorry, say that one more time. I didn't hear you.
Mapn in Scala is the same thing, like with a dollar sign, with how you combine it to the validated?
That's functor map, so it would be just map in Scala. So you are mapping the partial function, so you have a function that's just A to B to C up top, where your A is your email address, your B is your password, and your C is your validated form. And you are mapping that function that's A to B to C in no structure, no other context, into the V context and feeding it the first value output of your validated function. And then with apply, you're carrying that through and you're fully realizing the application. But the reason why you can't use map again is because you're already in the structure of V. So you need to use a function that knows how to carry it through the structure and apply it. So this is the whole function. And I think that this is especially neat because this is a pretty short implementation. What you're basically doing is you are encoding the optionality, the indecision around whether or not you're going to get a valid result entirely in these type class abstractions that we've defined earlier. You're building up incrementally a validated form from these pieces, but you haven't had to write a whole lot of, I would say, specific logic around doing a bunch of error checking to make sure that you're adding things in the right places. You're relegating all of that to the type class instances and using these common abstract operators to sort of glue it all together. So,
You would use this to make a smart constructor.
you wouldn't.
Passing form data.
You wouldn't necessarily, I think, even have to, because
Use this the way it is.
yeah. So the unvalidated record is your constructor, and you just apply this function to the unvalidated record. So if you were, for example, building this from a website and you were able to get your form data from a website and then dump all of the strings into a record. So like if you know what fields exist on your website or on your web page, you could pull those strings out and put them in there. You just apply that function to your record, and then you get back a validated record. You get back a V of either the errors or the validated record. Does that answer your question?
Yeah, it's beautiful.
So
I want it.
this is cool. What I think is really cool is that this is the legwork. I mean, like this is all of the legwork in terms of building up all of the complexity. Now you can add another field just by defining another field validation function and then slapping it on there with another infix apply operator. You could keep doing this as often as you want. You just need to make sure that the structure of your unvalidated form matches the structure of your validated form, that you have a specific function that can handle doing the validations, and then you just pass it through. You keep adding more fields to that record you're building up, and you keep adding more validation functions with the apply operator below it. And like that's basically your builder for these things, all expressed in terms of, I think, some pretty general abstractions. Is this all clear? Okay, so this exercise is a little more freeform. We got, I guess, an option here. Does everyone here want to try and do this exercise before taking a break, or take a break, maybe get something to drink, use the restroom, come back and run through it, because we're about halfway.
I think I was supposed to do it.
Yeah, I mean, I can leave it up. Anyone who wants to take a break can take a break, and anyone who doesn't can try and work through this. I think it's going to be a little more difficult and be a little more free form, so I can also walk around and help people out if they run into anything complicated. So how about we make sure we're back here to go over this around about 2:15 or 2:20 or so. Sound good? And then if we all finish earlier, then we can go over it earlier.